Okay, for this problem, we have two blocks. We're given the coefficients of friction, and we're given a force. We're asked for the acceleration of each block. First thing to do is to try to identify whether or not you need to use a free body diagram for this problem. So you look to see what it is that they're asking for. They want the acceleration. So we want the acceleration of both blocks. So it's not a dead giveaway. So the next thing you do is count the degree of freedom. And if the number of accelerations that you're given equals the degree of freedom, you don't need a free body diagram. So anyway, let's just take a look at this. And so you say, what's the degree of freedom? Well, in this case, it depends. It depends on whether or not the blocks are sliding. Now, yes, it would be a silly question for the author to ask if the blocks are sitting still, right? So you're probably pretty sure that something's going to move. But anyway, in the real world, you wouldn't know that. You wouldn't know if the force P is large enough to move it or not. So anyway, the point is that you're going to have to make an assumption about this because you don't really know what's going on. Okay, so the way you should start assumption problems is make a table, and you're going to list what your assumption is, and then beside each one you're going to count the degree of freedom, assuming that your assumption is correct. So what are the things that could happen? Nothing moves. No motion, right? They both stick. If they both stick, the degree of freedom is 0. If that's not the case, what else could happen? Well, A could slide, but B stick. Right? That could happen. If that's the case, you have a degree of freedom of 1. The next thing that could happen is A could stick and B slides. That could happen. If that happens, the degree of freedom is 1. Last thing is that they both slide. If that's the case, then the degree of freedom is 2. Okay. Now you don't really know which one is happening, and so therefore what you want to do is you've got to pick one. You should always choose the minimum degree of freedom to start with. The reason for that is that if it has smaller degree of freedom, there's going to be fewer unknown accelerations, and acceleration is the hard part in dynamics. So you should start there because the problem is a little easier, plus the fact that for minimum degree of freedom there will be more constraint forces, because in order to reduce the degree of freedom you have to introduce constraints. That's what constraints do. And so for every constraint there's going to be a force of constraint, and those forces you calculate, and those constraint forces will tell you whether or not your assumption is true. Okay, so what you're going to do is, in this particular case, you have 0 degree of freedom. Now, if the assumption is true, you can tell me right now what's the acceleration of two blocks. Oh, it's easy. If in fact my assumption is true, the acceleration of A is 0 and the acceleration of B is equal to 0. Boom, problem solved. Go to the next problem. Okay, but stop. You've got to determine whether or not this is true. How are you going to do that? You're going to calculate the constraint force. What's the force that's holding it at rest? It's the friction. So what you're going to do is you're going to calculate the friction force. That's the constraint force. That's the force that's holding it at no acceleration. When you calculate those things, then you're going to ask the question, is it possible for me to get this constraint force or not? I'll show you some details. Okay, so what you really want to know now to check your assumption is you need to know what are the constraint forces. Aha, dead giveaway, it's a free body diagram problem. Okay, so I have to draw the free body diagram. Now, what I'm interested in is the friction forces between the two blocks and between the table and the block. So I'm going to draw two free body diagrams. I could put them together because A and B have the same accelerations. That's possible, but because I want the two friction forces, I want to draw the two bodies separately. So here we go. We're going to draw A. First thing I'm going to do is put in the action at a distance forces. So I have gravity. And let's see, do they give me the masses? Let's see. Block B rests on smooth surface. Oh, okay. Well, I didn't catch that. B is on a smooth surface, so there is no friction. I'm going to do a harder one. I'll say that there is friction down here and just show you what happens. Okay. So in this case, you have mass A times G. And then you look for contact. The only thing that you have contact from is the force P. Well, don't say only thing. You have this force P, and you also have contact between A and B. So you have a normal force here. We'll call it NA. That's the pressure that's being put onto A. And then you have a friction force. Okay, so I'm going to draw it in. It's parallel to the surface. It's static, so I don't really know what the magnitude is, so I'm going to label it as FA. Now, if this thing is going to slide, if A is going to slide, it's going to go to the right. If you push on it over here with this P, you're going to shove it to the right. So if it slips, it wants to slide to the right. And so that is being held, friction opposes that, so it's going to hold it back this way. Okay, so that's a free body diagram of A. Are there any other forces? Look for other contact. There's no other contact, so therefore that's all the forces. Then you draw a free body of B. We'll go ahead and do that one while we're at it. It has an action at a distance force. It has mass B times G. And then anything else, yeah, look for contact, anything touching it. Yeah, the force touching it, so we're going to call it a pressure, right, NB. And then it says it's smooth, but I'm going to make it a little harder. I'm going to draw in a friction force here. If it's sitting still, it's static. I'm going to call it FB. Now, if B slides, it's going to also go to the right. So I'm pretty sure that this guy comes back to the left. Any other contact? Yeah, A is touching. So what you're going to do is you're going to draw this guy in here. This guy is going to be the pressure between A and B. I've already drawn that. I've called it in A, so I have to call it the same thing. Notice that it's equal and opposite. It's equal to NA, but it's down instead of up like the other one was. And then there's going to be a friction. And because FA was pointed left, this one has to be pointed to the right. Okay, they have to be equal and opposite. Okay. After you draw the free body diagrams, the next thing that you do is you sum forces. You have to decide at this point what direction to sum the forces in. You should always choose the direction that makes the acceleration as easy as possible. Well, in this case, it'd be horizontal and vertical. So what I'm going to do is I'm going to sum forces positive to the right and positive up. So those are my two directions. Okay, so here we go. We're going to do horizontal forces for A first. So that would be P minus FA. That's all, and that equals the mass of A times the acceleration of A in the horizontal direction, which is 0. Why? Because of the assumption you're assuming no motion, right? So that's why it's 0. Some vertical forces, you have NA minus MAG. That's all. That equals 0. Students will oftentimes say, oh, well, I know what the N is, and they'll write it down. That's okay. Just be careful, because if the table was moving, if the table was accelerating upward or something, the normal force would not equal the gravity force. Okay, so just be careful. Okay, so let's sum forces on the body B. On body B, horizontally, FA minus FB. That's all. That equals mass times acceleration. It will be mass B, is the mass that's in the free body, times the acceleration of B horizontally, which is 0 because of my assumption that everything is stationary. Sum forces vertically, you have NB minus MBG. minus NA at equals 0. It's the vertical acceleration. Okay, so now let's circle the unknowns that we have. They tell me P. I don't know the friction of A. It's less than or equal to mu n. I don't know NA. Now, some students will say, well, I know NA. Well, if you say that, then you cannot count this equation, because that's all that equation does, is tell you what NA is. So either you count NA and count the equation, or you leave it out. I count everything. That way I don't have to worry about, what should be counted, what shouldn't be counted. Okay, so I don't know FB, and I don't know NB. So there's 4 unknowns and 4 equations. Can these be solved? Absolutely. So what I'm going to do is pause. I'm going to pull up Mathematica, and I'm going to go ahead and solve these things. Okay, what I've done here is pulled up Mathematica, and I've typed in the equations. You can see them over here in the equations. EQN is my equations. The curly brace means that this is a set of equations. Remember that when you write an equation, this is 2 equal signs that you type to indicate that it's an equation. So anyway, these are the equations, and you can see that they match up over here. The only thing that's different here, that I added, is I've added in what the maximum friction force can be on A, and the maximum friction force can be equal to mu s times the normal of A. The maximum B friction could be mu s times NB. Now, what I'm going to do to check my assumption is I'm going to solve for the friction of A and the friction of B, and I'm going to make sure that those numbers are less than or equal to the maximum values. And if they are, then I know that my assumption is correct, that I have plenty of friction to hold it in place. If they're invalid, then I know that I've made a mistake. Okay, so what I need to do now is to put in numbers that correspond to the values of gravity and mass, coefficients of friction, etc. So let me pause and type that in. Okay, so here what I've done is I've solved the equations, and I'm calling the solution the answer. This is before I put in the numbers. So I'm just solving my 6 equations for the 6 unknowns. Friction A, friction B, normal A, normal B, friction A max, friction B max. And so I end up with these formulas. And you can look at those if you want, but maybe the easiest thing to do is plug in numbers. Now, I know I'm using the wrong P, but what I'm doing is using a small p to show you what will happen if the assumption is valid. So I'm putting in a force of 1. Mu s is equal to 0.4 from the problem. G in feet is 32.2. The mass is the weight, which was 20 pounds, divided by the gravity. Mass of B is 50 over gravity. And so then I just take these numbers and plug it into the answer, and here's the numbers you get. So the friction A, in order for the assumption to be valid, you have to have 1 pound of friction under A. Under B, you have to have 1 pound of friction. You have your normals, no big deal there. The maximum value that you can get for friction under A is equal to 8 pounds. So you only need 1 pound, and you're able to get 8 pounds. So definitely that one will not slide. And then again, under B, you need 1 pound, and you can get 28 pounds under there. It's because you've got all of the weight that's pushing down on that, increases the pressure under it. So in this case, the FA is less than FA max, and FB is less than FB max, and so therefore the assumption is valid. Now what I'm going to do is solve exactly the same problem, but this time we're going to put in the pressure, the force of 8 like it was before. So I'm going to pause and do that. So here what I've done is I've changed the value of P to 8, which was what was given in the problem. And if you notice now, the friction that's required under A has to be 8 pounds. And so A is exactly equal to 8 pounds. And so this would be what they call impending motion. The slightest bump on this thing would cause it to begin to move, and once it moves, the friction would become kinetic, and it drops lower, and A would actually accelerate. In this case, if there was friction under B, B would stick to the floor. So here, what I would say is that A is really going to move. I mean, because it's not going to hang there forever, so it'll probably end up sliding. So if a situation like this, if this were on a test, I would say, okay, it's impending motion, it won't slide, and there's no motion on this. But realistically, the thing's probably going to rip loose and start sliding. If you do that, then you'd say, okay, well, the assumption that no motion isn't valid, and so which one of these would you do next? Back over here on this one, you should take, if it's not 0 degree of freedom, right, no motion, which one is it? Well, it looks like, based on the numbers that you got, that A is going to be sliding, but B is still sticking. So what I would do is I would take this one next and analyze that one to investigate this. So that's what you would do, and you would continue to do this until you find an assumption that's valid. Okay. What I plan to do now is do the problem the way they say, where there's no friction under B. So let's take a look at what changes for that one. Okay, so here we have, we're still going to draw a free body diagram. Do you believe that A sticks to B and they slide? So in other words, this one, so it's possible, let's put this in different colors, possible that this could happen. Well, no, I'm sorry, if there's no friction under B, that one can't happen. This one can't happen because B will definitely move, right? A could be sticking on B and B slides, or it's possible that both A and B both slide. Okay, so these are the two assumptions. And which one is which? Well, what you should do always is, if these are your two choices, always begin with the minimum degree of freedom. So we're going to begin with 1, the freedom of 1. What we're doing is we're saying A is sticking to B and B is sliding. That's what we're going to assume. Okay, let's take a look at the equations. Let's take a look at the free bodies, okay? What changes in the A free body? Nothing, really, because you're assuming A is sticking. So there's static friction up here on A, so it's static friction just like before. If A does slide, it will slide to the right, so nothing is changing up here. What's changing on the B free body diagram? Well, on B, this guy here is not static anymore because you know it's sliding. Well, I did it again. Okay, if it was had a friction, this thing would become UK times NB. You know what the magnitude is, so that would be the change. But in this case, there is no mu k, so this guy here is completely 0, right? Keep forgetting it's a smooth surface. Everything else is exactly the same as it was before. Let's take a look at the equations. What changes in the equations, okay? So in this particular case, in the for the top guy, the mass times acceleration, the forces don't change. They're the same free body as it was before. But now what's going to change here is this is equal to the mass of A. It's the mass that's in the free body diagram, mass of A, times the acceleration of block A in the horizontal direction. I think it's going to go to the right. That's why I put it in as a positive MA. If I solve for A and I get a positive number, the direction I thought it was going is correct. If I get a negative for the A, the direction I thought was wrong. Okay, so what I'd like to do is I like to say it's always going to the right. So I put it in as a positive MA. So that's a change there. What changes down here for the vertical? Nothing. How about this? The equation forces on the X. Okay, what's changing here is that if there was a friction, right? If there was a friction, this thing would be mu k in B. Everything else is the same. Excuse me, the mass times acceleration. It's accelerating, so it would be the mass that's in the free body diagram, mass B. That's what's in that free body, times the acceleration of B. Okay, so let's just kind of keep our eye on this term right here. I'm going to show you what happens because it's smooth. That guy's 0. Okay, and you sum forces vertically, nothing changes down there. Now, if you circle the things that are unknown, You still don't know FA. You don't know acceleration of A. You don't know NA. You don't know the NB. But what happens here, and I'm going to circle the AB right here. Okay, now, what happens is if you count the number of unknowns, there's 1, 2, 3, 4 from this acceleration, 5 from this guy. But notice this guy used to be an unknown. This guy right here. It used to be FB, and that was a circled unknown. So when they begin to slide, you no longer have that unknown constraint force. That was an unknown constraint force. It doesn't exist anymore because it's sliding. So whenever you add freedom, the constraint force disappears, right? So here, that constraint force disappears that you had to solve for before. Now it's no longer there. Okay, so that's what's going to happen. All right, so that's a 0 there. So that's why I crossed it off. Okay, but it looks like you have 1, 2, 3, 4, 5 unknowns. Now, it's pretty obvious, I think, that everybody knows that these guys are equal, right? But here's what is, in general, going to happen. It's not uncommon for you to have more unknowns than you have equations, okay? Now, what you want to do is be able to determine what kind of equation am I looking for? Am I looking for another force equation? Am I looking for a free body diagram? What am I looking for? Okay. So what you do is you look at the number of degree of freedom. The degree of freedom of this is 1. It's 1 degree of freedom. What that means is there should only be one unknown acceleration. How many unknown accelerations do you have? It looks like, if you kind of put your brain at ease, it kind of looks like you got 2. You shouldn't have 2. You should only have 1. What that means is, because it's 1 degree of freedom, if you know one of them, AA or AB, doesn't matter which one, if you know one of them, you should be able to find the other one. They are connected. They are related to each other. That's what 1 degree of freedom means. Okay, so obviously I should not have 2 accelerations. Well, of course not, because really what you're saying is that A is sticking to the top of B. So if A sticks to B, then they have exactly the same acceleration. So what that means is, here's another equation. It goes AA equals AB. They're related, right? So how many equations you got? You got 5. How many unknowns? 5. So everything's going to work out here. I'm going to pause. I'm going to pull up Mathematica, and we're going to solve it using that. Okay, so here's the Mathematica input over here. So the equation, EQN, I've typed in the equations. This is the first one, the forces in the x direction for A. Here's the vertical on A. Here is the forces, the horizontal forces on B. And this is the vertical for B. And then the relationship between the 2 accelerations, that they're equal. And then again, because you believe that they are constrained to go together, that A is not sliding on B, there's a constraint force. That's the FA. And so we're going to check the constraint force and make sure that it is enough or it's not too much to where the thing actually slides. So here are the equations that we have. And you hit enter, and then I solved them. So here is the solution for them. So let's take a look at it, right? So the friction force that's under A, if it does in fact stick, has to be 5.7. The acceleration is 3.68. The normals, the acceleration of B, the same as A, 3.68. The maximum friction that you can get under A is mu s times n, so it's still 8 pounds. So the question is, does it slip or doesn't it slip? It does not, because what you have to have is you've got to have 5.7 pounds of friction to keep it from sticking. And you can get that. You can get as much as 8. So the conclusion is your assumption is valid. A sticks to B. The acceleration of A is 3.68. The acceleration of B is exactly the same thing. So that's the solution. Now, if this number, FA max, had been too small, let's say it was 4, then you would conclude that you have to have 5.7 in order to stick. You can't get that, And so what do you conclude? You conclude that A doesn't stick to B, it actually slides on B. And then you would know exactly what it does. You would go back in for the next one, and you would say, if this guy was out, if A doesn't stick, therefore it slides. There's nothing left to check. And what would happen is this equation right here would not be valid, because if A is sliding on B, you should have two unknown accelerations, and they're not related to each other. But what does happen is if A is sliding, then this thing here is mu k times NA, and so it's one less unknown, one less thing. So how many unknowns would you have if you were doing the 2 degree of freedom? You'd have 4. AA, AB, NA, NB, and you'd have 4 equations. So it's solvable that way as well. Okay, that's it.